Hi. Okay, so slightly irritating. My recording software tends to crash, so it just crashed. So we have a part four rather than just a part three. We're going to talk about the gravitational path integral. Okay, and the gravitational path integral is an integral over metrics of e to the I action, and it's extremely mysterious because we don't understand quantum gravity. In AdS, when we do this path integral, we should do it with respect to some fixed boundary metric. If we had other matter fields in here, we would integrate over them, and we would fix their boundary conditions on the boundary as well. I haven't really talked about this very much here, but all the solutions we've written down have a boundary metric that is that of AdS, except we may have toroidally compactified it. But one could more generally ask for solutions of the Einstein equation where the boundary metric here is something different. Maybe we take time across the sphere, which has, say, the AdS or AdS-Schwarzschild as an interior, but we could then ask, supposing I try and deform the sphere and have that boundary metric, well, the CFT can certainly live on that space. So what's the gravitational description? And it's some deformation of AdS. You can do these sort of calculations. We won't go too much into it, but the key point here is that this object semi-classically, whilst we can't do this, we can understand semi-classically that this should be dominated by a saddle point. And so in gravity, we can approximate this, at least semi-classically, by e to the I action evaluated on a saddle point solution, and this we might call the on-shell action because it's evaluated on some solution, and that solution should be the dominant saddle point for this whatever situation you're in. And in AdS-CFT, this path integral here is the way AdS-CFT works, is to say this path integral is the path integral of the CFT. This condition, the boundary condition that you fixed in your gravity, is, from the CFT point of view, telling you what space the CFT lives on. If you have other matter fields in here and you have other data here for them, the boundary conditions here, it turns out that translates into sources for various operators over here. So, and this is called the AdS-CFT Dictionary. I don't want to talk about it too much, but one thing I would say is that in field theory where you've got a path integral as a functional of something, you functionally differentiate with respect to it in order to generate correlation functions. And here we could ask, supposing we could construct the bulk solutions as a function of this boundary metric, we could functionally differentiate with respect to them, evaluate everything, say, with a saddle point approximation, but certainly in principle, we could do this. What are the correlation functions we're generating? Well, we're generating precisely correlation functions of the CFT stress tensor. That's what the AdS-CFT Dictionary tells us. In fact, the two-point function can be got this way. And you can think about that by doing sort of perturbation theory about AdS. And it is precisely that calculation that tells you actually how to relate the central charge of the CFT, which comes into the two-point function, to the Newton constant in the bulk. So that's a sort of important calculation. But anyway, let's now just focus back on the gravity. How might we calculate this? How might we calculate this object? What is the gravitational action? Well, let's go to the Euclidean setting. And then actually we can think of this as, well, it's not only, really it's a function of the Euclidean boundary metric, but we can think of it as being a functional of temperature, because in the boundary metric, we've got a compact Euclidean time, which we can think of as changing the size of, giving it size beta, and that's the inverse temperature. So in the Euclidean setting, this really is like a partition function. And then in the saddle point approximation, what we want is we would evaluate this by some saddle point solution, the Euclidean action, the Euclidean gravitational action evaluated on a saddle point solution would give us our partition function. Again, this is the partition function then of the CFT at that temperature. So this should be equal the partition function of the CFT at temperature 1 over beta. So it's an interesting thing to calculate. How do we calculate it? Well, the Euclidean gravitational action is the following. So if I've got some manifold M, this so very generally, this would be my Euclidean gravitational action. There's the Einstein-Hilbert term. There's some matter terms if I've got them. But there's also one more term here called the Gibbons-Hawking term, where if I have a boundary in my geometry, I have to add on this Gibbons-Hawking boundary term, which makes the variational problem well defined. Hawking term. So this, it's a very interesting term. Well, let me just tell you what it is. I mean, of course, this is the usual. This is the spacetime determinant of the metric. It's Euclidean, so there's no minus sign. This is its Ritchie scalar. This is the induced metric on the boundary. So the boundary, let's say near the boundary, let's write the metric like this. Where the boundary is at rho equals rho boundary. And so so these are then Gaussian normal coordinates to that boundary. We're not talking about AdS, this is just completely general. So we've just got some boundary in our space. We use Gaussian normal coordinates to the boundary. H here, then H mu nu at rho boundary. Let me just call it rho b dx mu is the induced metric on the boundary, and it's this which you take the determinant of to get this root h, and k is the trace of the extrinsic curvature with respect to that metric. This is the extrinsic curvature, or so-called second fundamental form, and it's defined in coordinates like this as half d by d rho of the metric, this function in here. So it would be, obviously, this is this trace here, this evaluated at rho is rho b. So if you like, this is the extrinsic curvature evaluated on the boundary, okay, where the trace is taken with respect to the metric on the boundary. Note, I should just say where, let's say we've got rho here, and this is our interior, and this is rho b, where we think of d by d rho equals the outer normal, the outer unit normal to the boundary, meaning it's pointing in the going out of the geometry. So here our boundary is at, say, rho is 0, then the actual space-time is at negative rho. You've just got to be careful of signs, because when you compute these things, you've got to get the sense of the direction of rho right. So generally here, this is like a derivative of the metric in these Gaussian normal coordinates with an outward normal derivative. Okay, that's how one computes that Gibbons-Hawking term. And so if you, now how does it work in an AdS space? So this is in a general space. So in an AdS space, or a Euclidean, let's say Euclidean AdS space, so actually a hyperbolic like space, we don't have a boundary, we've got a conformal boundary. Now this diverges. The action diverges. So that's a bit awkward. But actually, if you think about a CFT and you calculate its partition function, it's also divergent, and you have to renormalize it. And so in exactly the same way, you have to renormalize the gravitational action in AdS. How do we do that? Well, we regulate it, and then we add counter terms and remove the regulator. And if our metric looks like this, as before, we can write it, say, we can write it in terms of some defining function and some regular metric. So this is now regular. So this is our, this has a conformal boundary. This is a regular metric with a real boundary. And, you know, and z is greater than 0. Z is 0 is the conformal boundary. And what we do is we cut off the spacetime so that instead of the full spacetime is sort of in z from 0 up to whatever it goes up to, maybe a horizon or infinity. But here we cut off the spacetime we regulate it to go from epsilon only, where epsilon is some positive number, and then we'll take epsilon to 0, and so this regulates the path integral or the partition function. Okay, so now it's finite. So now our regulated Euclidean action looks like this. Now for AdS, we don't have general matter. We're only integrating over for z greater than this cutoff. The only matter we've got is a cosmological constant, and so the form of the Einstein-Hilbert action is this. We should include our Gibbons-Hawking term, which is now evaluated at this boundary. So I should compute the extrinsic curvature of that boundary. It's induced metric on that boundary, epsilon. That boundary will get very big as I take epsilon to be small, but nonetheless that term should be there. And then this is my Euclidean action, and it's now finite provided epsilon is positive. As I take epsilon to 0, it'll diverge, and so I have to add counter terms. And those counter terms, if I tune them correctly, I can remove the divergences as epsilon goes to 0. So these remove divergences as epsilon goes to 0. And what do those counter terms look like? Well, they are dimension dependent in, well, basically they take this form. So in odd dimensions, they are nicely written, most nicely written, as integrals of curvature invariance, local curvature invariance on this boundary. And so in 3 dimensions, you only need, the divergences you have there are only 2 divergences you need and 2 counter terms to subtract them, and these constants a and b have to be suitably chosen and determined to remove the divergences and all of this as you take epsilon to 0. And again, this here, h, is this induced metric on this boundary here. And these are the counter terms you need in d equals 3. In odd dimensions, say d equals 5, you would need another counter term with sort of r squared like form in. And in even dimensions, it's slightly more complicated because there's a log term that you can't quite write covariantly like this. And so there's a sort of log epsilon times some curvatures. It's slightly more complicated. Again, have a look at Kostas Skenderis's lecture notes if you want to understand a little bit more about how this works, although there are some subtleties in these calculations. I'm doing things slightly differently to how he did in those lecture notes. Now, as an example of this, so once you've computed this, regulated it, chosen these appropriately, you can take epsilon to 0 and get something finite. So the last problem on the example sheet is to do that in the case of global AdS-Schwarzschild. It's a subtle calculation. Try it. And then as an example, the free energy, beta times the free energy, is minus log of the partition function, evaluated at that temperature, you know, in StatMech, or thermodynamics, I should say. And using a saddle point approximation, this is just the renormalized Euclidean action. So this is using the saddle point. So using this here, or rather this here, taking the log of this, I just get minus the Euclidean action. And so if I calculate this, if I calculate this fella here, I should be computing, that should allow me to calculate the free energy. And this should agree with the free energy as calculated, for example, if you calculate the entropy, temperature, and energy, maybe from the stress tensor, or even more slick, calculate entropy, temperature, use the first law to get the energy, then you can get the free energy from this relation, and that should all agree with this. Okay, and so maybe have a go at calculating this for one of these solutions. More generally, as you've probably seen, if you're looking at the archive over the last year or so, or a year or two, there's been all sorts of interesting progress in thinking about Euclidean, the Euclidean semi-classical approximation related to entanglement entropy, islands, and so on. But this is a sort of very basic calculation with the path integral. Or saddle point approximation to a path integral in gravity that you would have to sort of learn in order to go on to more complicated things. So hopefully, if you've seen some of this stuff before, there's some stuff that you haven't seen or haven't tried, have a go at some of the calculations. If you haven't seen any of this, hopefully at least some of the earlier parts were of some use. Okay,